Right now, physicists at the Large Hadron Collider routinely accelerate particles to 99.9% of the speed of light and far beyond. At peak energy, a single proton in that machine carries the kinetic energy of a flying mosquito compressed into a space 1 trillion times smaller than a grain of sand. Now imagine scaling that kind of energy up to an entire spacecraft. The energy required would exceed everything human civilization has produced in 3,000 years. Time on board would slow to a crawl while decades vanish on Earth. The space ahead would compress into a blinding point of lethal radiation, and a single grain of interstellar dust would strike with the force of a bomb. This is not science fiction. This is what Einstein's equations guarantee. The question is whether anything could survive it. If you want to see what really happens when physics reaches its most extreme and beautiful limit, hit that like button and subscribe. Now, settle in and get comfortable. Let's begin. Let us start with the number itself, because the number is where everything begins to break. 99.9% of the speed of light. Say it out loud, and it sounds almost casual, almost there. Just a hair short of the ultimate cosmic speed limit. You might hear that figure and think it is barely different from light speed itself. After all, it is only 0.1% away. How much could that tiny gap possibly matter? It matters more than almost anything else in physics. The speed of light in a vacuum is approximately 186,282 miles per second. In metric terms, that is roughly 299,792,458 meters per second. Scientists refer to this value simply as c. It is the fastest that any signal, any particle, any scrap of information can travel through the fabric of space-time. Nothing with mass has ever reached it. Nothing with mass ever will. 99.9% of that speed works out to approximately 669 million miles per hour. At that velocity, you could circle the Earth's equator more than 26,000 times in a single hour. You could reach the moon in barely over a second. You could cross the distance between Earth and the Sun in roughly 8 minutes and 20 seconds, which is almost exactly how long sunlight itself takes to make that journey. At 99.9% of c, you are moving so close to the pace of a photon that the difference is almost too small to measure with everyday instruments. But physics does not care about what sounds close. Physics cares about what the equations produce, and the equations produce something extraordinary at this threshold. To understand why, you need to meet one number that controls everything that happens at relativistic speeds. It is called the Lorentz factor, and at 99.9% of light speed, it changes the rules of reality. The Lorentz factor is calculated by taking 1, dividing it by the square root of 1 minus velocity squared over c squared. For speeds we encounter in daily life, this factor is so close to 1 that it might as well not exist. A commercial airplane cruising at 550 miles per hour has a Lorentz factor that differs from 1 by roughly 1 part in a trillion. Even the International Space Station, hurtling around the Earth at 17,500 miles per hour, has a Lorentz factor of only about 1.000000003. The effects of relativity are real at these speeds, measurable with atomic clocks, but utterly imperceptible to human experience. At 90% of light speed, the Lorentz factor climbs to roughly 2.3. Things start getting noticeable. At 99%, it reaches approximately 7.1. The effects are now dramatic, but at 99.9%, the Lorentz factor leaps to approximately 22.4. That single number, 22.4, is the key to everything that follows. It governs how time stretches, how distance compresses, how energy skyrockets, and how the universe itself appears to reshape around a traveller moving at this speed. Every bizarre consequence of near-light travel traces back to this factor, and at 99.9%, it is large enough to transform physics from a set of subtle corrections into a set of violent distortions. Here is the first thing the Lorentz factor does. It changes what an outside observer sees when they look at the ship. Imagine you are standing on a platform in deep space, perfectly still relative to the surrounding stars. A spacecraft streaks past you at 99.9% of light speed. What would you actually observe? The first thing you would notice, if your instruments were fast enough to catch it, is that the ship appears compressed along its direction of motion. This is not an optical trick. It is not caused by the delay in light reaching your eyes from different parts of the ship. This is a genuine physical prediction of special relativity called Lorentz contraction, and it is measured, not merely perceived. A spacecraft that is 100 meters long at rest would measure only about 4.5 meters long to your instruments. As it passes at this speed, the ship is physically shorter in the direction of travel as measured in your reference frame, not because anything has been physically crushed, but because the geometry of space-time itself behaves differently at relativistic velocities. Think about what that means for a real ship. A vessel the length of a football field, built to carry crew and cargo across interstellar distances, would appear no longer than a large car to a stationary observer watching it pass. Every internal dimension along the direction of travel, the corridors, the laboratories, the cargo bays, would appear squeezed into a sliver, yet the crew inside would notice nothing unusual about their surroundings. Their ship would feel exactly the same length it always was. They would float through the same corridors, open the same doors, and measure the same distances with their rulers and laser beams. The contraction is real, but it exists only from the perspective of someone in a different reference frame. This is the first hint of the conceptual split that defines everything about relativistic travel. There is no single answer to how long the ship is. There is no single answer to how far apart two stars are. There is no single answer to how much time has passed. The answer depends entirely on who is asking and how they are moving relative to the thing being measured. Special relativity does not say that one perspective is correct and the other is an illusion. Both are physically real within their own reference frames. The universe is not playing favorites. It is enforcing a deeper consistency that human intuition is not built to handle. Now consider what light from the ship looks like to your instruments as it passes. The ship is radiating in all directions. It carries running lights, emits thermal radiation from its hull, and perhaps broadcasts radio signals. At 99.9% of C, the light from that ship does not arrive at your sensors the way you might expect. Light emitted from the front of the ship, in the direction of travel, gets compressed in wavelength. This is the relativistic Doppler effect, and it is far more extreme than the Doppler shift you experience when an ambulance drives past you with its siren. At this velocity, visible light emitted forward would be blue shifted into the ultraviolet range, possibly even into X-ray frequencies. The ship would not appear as a visible object ahead of itself. It would appear as a concentrated source of high-energy radiation compressed into a small angle centered on its direction of travel. Meanwhile, light emitted from the rear of the ship gets stretched. Visible light shifts down through red, into infrared, into microwave frequencies. An observer standing behind the ship's trajectory would detect almost nothing in the visible spectrum. The ship would appear to vanish into radio silence as it receded. This bunching of light toward the forward direction is called relativistic beaming, and it has a dramatic visual consequence. If you could somehow capture the entire electromagnetic output of the ship as it passed, you would find that the vast majority of its energy is concentrated into a tight cone, aimed directly ahead. The ship becomes directional, a flashlight screaming through the cosmos, broadcasting most of its energy into a narrow beam while the space behind it goes dark. But there is something even stranger happening to the way the ship looks. Something that was predicted more than 60 years ago, but was never directly observed until recently. In 1959, two physicists working independently reached the same surprising conclusion. Roger Penrose in England and James Terrell in the United States both realized that a rapidly moving object would not actually appear flattened to a camera or an eye. Even though Lorentz contraction is real and measurable, The visual appearance of the object differs from the measurement because photons from different parts of the ship arrive at your eye at different times. Light from the far side of the ship left earlier than light from the near side, which means your snapshot captures photons that departed from different locations at different moments. When your brain or your camera assembles those photons into a single image, the result is not a flattened ship. It is a ship that appears rotated. This is called the Terrell-Penrose effect, and for more than 6 decades it remained purely theoretical. No one could photograph it because no one could accelerate a macroscopic object to a significant fraction of light speed in a laboratory. The energies required are absurd. But in 2025, a team of physicists at the Vienna University of Technology found a way around the problem. They used ultrafast laser pulses fired in sequences of about 1 picosecond each, combined with precision-timed high-speed cameras, to simulate what a camera would record if an object were moving at 99.9% of light speed. They physically contracted a sphere into a disk to mimic Lorentz contraction, then illuminated it slice by slice, shifting the object between exposures to reconstruct the light arrival pattern a real camera would capture. The result confirmed the prediction exactly. The contracted sphere still appeared round in the photograph, but parts of its far side were now visible, as though the sphere had been gently turned. A cube treated the same way appeared rotated rather than squashed. The images were striking. For the first time, a prediction of special relativity about the visual appearance of near light speed objects had been recorded experimentally, using physical objects in a laboratory. This experiment matters for our story not because the Terrell-Penrose effect is the most dramatic consequence of relativistic travel, but because it illustrates something essential about the physics. Even the way things look at these speeds defies everyday expectation. Your intuition says that a compressed object should look compressed. Relativity says otherwise. The geometry of light arrival reconstructs the image in a way that preserves apparent shape while revealing hidden surfaces. Reality at this speed is layered. The measurements say one thing, the photographs say another. Both are correct, and both are consequences of the same underlying physics. Now extend this to the broader visual field. The crew is not just emitting light, they are also receiving it. Every star, every galaxy, every photon drifting through interstellar space interacts with the ship's motion. The relativistic Doppler effect and aberration do not apply only to the ship's own emissions. They reshape the entire sky. From the perspective of a stationary observer watching the ship, something eerie happens to the starfield. Stars ahead of the ship appear bunched together, crowded into a smaller and smaller region of the forward sky. Stars behind the ship appear spread apart and dimmed. This is relativistic aberration, and it grows more extreme as velocity increases. At 99.9% of light speed, the effect is so severe that nearly the entire sky appears compressed into a small, intensely bright disk, centered directly ahead of the ship. The rest of the sky, the hemisphere behind and to the sides, goes almost completely dark. Virtually all incoming starlight has been swept forward by the ship's motion through space-time. The light in that forward disk does not look normal. The Doppler effect shifts star colors drastically. Stars that would normally appear white or yellow are now radiating in the ultraviolet or X-ray range. Infrared sources ahead are boosted into visible light. The forward sky becomes a concentrated furnace of high-energy photons, compressed in both angle and wavelength, pouring radiation into the ship's path with an intensity that would overwhelm any unshielded detector. Meanwhile, the cosmic microwave background radiation, the faint afterglow of the Big Bang that uniformly fills all of space, at a temperature of about 2.7 Kelvin, does not remain faint. From the ship's reference frame, this microwave radiation gets blue shifted in the forward direction. At 99.9% of C, the Lorentz factor of 22.4 means the effective temperature of the cosmic microwave background directly ahead of the ship climbs to roughly 120 Kelvin. That is still cold by everyday standards, but it represents a 44-fold increase, and the energy flux grows even faster because it scales with the fourth power of temperature. At even higher velocities, the blue-shifted microwave background begins to resemble dangerous radiation. The entire universe becomes a weapon pointed at anyone foolish or brave enough to approach light speed. All of this is what an outside observer can measure, calculate, and record. The ship is compressed, its light is beamed forward. The sky around it is distorted. The electromagnetic environment is violent and anisotropic, meaning it is radically different depending on which direction you look. None of these effects require exotic physics. None of them involve speculation or hypothesis. They are direct, confirmed consequences of special relativity applied at a Lorentz factor of 22.4. But here is the critical conceptual point that must be established before we go any further. Everything described so far belongs to the observer's reference frame. The stationary watcher measures the ship's contraction. The stationary watcher detects the beamed radiation. The stationary watcher records the aberrated star field. These are real physical effects within that frame. The crew on board the ship inhabits a completely different reality. This is not a metaphor. In special relativity, the distinction between reference frames is not a matter of perspective or opinion. Each frame has its own physically valid measurements of length, time, and simultaneity. Events that are simultaneous in one frame are not simultaneous in another. Distances that are constant in one frame are contracted in another. Durations that take years in one frame may take weeks in another. The universe does not provide a master clock or a master ruler that both frames agree on. It provides a set of transformation rules, the Lorentz transformations, that translate one frame's measurements into another's, and those translations preserve all the laws of physics while scrambling the intuitions of anyone who grew up at low velocity. The traveller's frame and the observer's frame are not two descriptions of the same events. They are two complete and self-consistent realities that happen to be connected by a mathematical bridge. Cross that bridge from the stationary observer's side to the crew's side, and everything changes. From the observer's frame, the ship is contracted to 1/22nd of its rest length. From the crew's frame, the ship is its normal size, but the entire universe is contracted along the direction of travel. Stars ahead are closer together. The distance to the next star system has been compressed by a factor of 22.4. A journey that measures 4.37 light-years from Earth's perspective measures only about 2/10 of a light-year from the crew's perspective. From the observer's frame, the ship's clocks run slow. A clock on the ship ticks once for every 22.4 ticks of an identical clock on Earth. From the crew's frame, their clocks run perfectly normally. It is the Earth's clocks that appear to run fast, though the situation is not perfectly symmetrical because the ship had to accelerate to reach this speed, and that acceleration breaks the equivalence between the two frames. This asymmetry is what makes the time difference real and permanent when the travellers eventually stop or return. From the observer's frame, signals sent by the ship arrive redshifted, stretched in wavelength, arriving slowly like words spoken in slow motion. From the crew's frame, signals from Earth arrive blue-shifted and compressed, squeezed into rapid bursts of high-frequency information. Two frames, two realities, one universe enforcing the same set of laws in both, but producing wildly different experiences. This is the conceptual foundation for everything that comes next. Without understanding that these two perspectives diverge, that they must diverge, and that neither is more real than the other, nothing about relativistic travel makes sense. Time dilation is not a clock malfunction. Length contraction is not a visual illusion. They are structural features of space-time itself, revealed whenever relative velocities become a significant fraction of c. At 99.9%, they are not subtle, they are dominant. They reshape every measurement, every observation, every physical process. And the reason this matters, the reason it is worth taking the time to establish what an outside observer sees before we even step on board the ship, is that most descriptions of relativistic travel skip this step. They jump straight to time dilation and treat it as a curiosity. They mention length contraction as a footnote. They hand-wave about twins aging differently and move on. But the physics is not a curiosity. It is a complete restructuring of how space and time relate to each other when velocities approach c. The observer's frame reveals the restructuring from the outside. The traveler's frame reveals it from the inside. Together, they form a picture that is both internally consistent and deeply alien to human experience. So far, we have stayed outside the ship. We have measured it, photographed it, analyzed the radiation it emits and the radiation it encounters. We have established that at 99.9% of the speed of light, the Lorentz factor of 22.4 transforms every observable property of the vessel and its environment. Lengths compress, light beams forward, the sky collapses into a searing disk of blue-shifted radiation. The ship appears to move through a universe that has been violently rearranged by its own velocity. Now, it is time to go inside, because what the travelers experience is not merely different from what the outside observer records. It is, in many ways, the opposite. And that opposition, that fundamental clash between two equally valid descriptions of the same journey, is where the real strangeness of relativistic travel begins. Step through the airlock and leave the outside observer behind. Everything we just discussed, the contracted hull, the beamed radiation, the collapsed star field, all of that belongs to someone standing still and watching the ship fly past. From the crew's perspective, none of it applies. Their ship has not changed shape. Their corridors are the same length they always were. Their clocks tick at 1 second per second, exactly as they did on Earth. This is not because the relativistic effects are imaginary. It is because the effects are frame-dependent. The crew occupies a different reference frame from the outside observer, and in their frame the laws of physics guarantee that everything local behaves normally. You cannot detect your own motion through empty space by conducting experiments inside a sealed laboratory. This principle, first stated by Galileo in the 17th century and elevated to a foundational axiom by Einstein in 1905, means that the crew has no internal measurement that reveals their velocity. Their hearts beat at the same rate, their food cooks at the same temperature. Light inside the ship travels at exactly c in every direction. If they did not look outside, they would have no way to know they were moving at all. But before the crew reaches cruise velocity, before any of the extraordinary relativistic effects fully manifest, they must first survive the long climb through acceleration. And this phase of the journey has its own distinct character that deserves careful attention. If the ship accelerates at 1g, a rate chosen specifically because it replicates the gravitational pull at Earth's surface, the crew experiences something remarkably familiar. They feel weight. Their feet press against the deck with exactly the same force as standing in a living room on Earth. A dropped coffee cup falls to the floor at the normal rate. A ball tossed across the cabin arcs in the expected parabola. For all practical purposes, the interior of the ship during acceleration is indistinguishable from a room on the planet they just left. But the ship is not oriented the way most science fiction suggests. During acceleration at 1g, the engine is below and the nose of the ship points upward, away from the direction of travel. The vessel functions as a vertical building with the engine as its basement floor. Crew members climb upward toward the bow and descend toward the engine. The entire architecture of daily life is organized around a thrust vector that mimics gravity so precisely that the human body cannot tell the difference. Einstein himself formalized this insight. His equivalence principle, the foundational idea of general relativity, states that acceleration and gravity are locally indistinguishable. A sealed room accelerating at 1g in deep space produces the same physical effects as a sealed room sitting on Earth's surface. The crew feels at home because, in a very precise physical sense, they are. This phase lasts a long time. At a constant proper acceleration of 1g, reaching 99.9% of light speed takes approximately 3.7 years of ship time. During those 3.7 years, the crew lives in a 1g environment, going about their routines under conditions that feel entirely normal. They exercise, eat, sleep, and work with bodies that function exactly as they did on the ground. There is no floating, there is no disorientation. The ship is a tall building accelerating through space, and the crew lives on its floors. Then the engine shuts off and everything changes. The moment acceleration ceases and the ship enters the cruise phase, weightlessness arrives instantly. 1G of comfortable gravity vanishes and the crew floats. This transition marks the boundary between the acceleration regime, where the crew feels force, and the cruise regime, where the ship coasts at constant velocity through space-time with no sensation of movement at all. The cruise phase may feel stranger to the crew than any relativistic effect, because it is the one phase where their bodies constantly remind them they are no longer on solid ground. But it is during this cruise phase that the universe outside the windows undergoes its most radical transformation. And the first and most visceral change is what happens to distance. From Earth's reference frame, the star Alpha Centauri sits approximately 4.37 light-years away. That number is a measurement made by astronomers who are essentially at rest relative to both the Sun and the Alpha Centauri system. It represents the proper distance between the two stars, measured in a frame where both endpoints are stationary. From the cruise frame, that distance does not exist. At 99.9% of light speed, with a Lorentz factor of 22.4, the space between the Sun and Alpha Centauri is compressed along the direction of travel by that same factor. 4.37 light-years divided by 22.4 gives approximately 0.195 light-years, roughly 2/10 of a light-year. That is the distance the crew measures between their departure point and their destination. To put that in more tangible terms, 0.195 light-years is about 1.15 trillion miles. That is still an enormous distance by any human standard, but it is roughly 1/22nd of what an Earth-based astronomer would calculate. The universe, as experienced by the travelers, has physically shrunk in the direction they are heading, not metaphorically, not as an illusion. The rulers they carry, the laser rangefinders they operate, the radar returns they collect, all confirm that the gap between them and Alpha Centauri is roughly 2/10 of a light-year. This is length contraction experienced from the inside, and it is the mirror image of what the outside observer sees. The stationary watcher says the ship is compressed. The crew says the universe is compressed. Both statements are correct within their respective frames. Neither contradicts the other, because they are measuring different things in different coordinate systems, and special relativity provides a precise mathematical relationship between the two. Now, combine this contracted distance with the ship's velocity. The crew is travelling at 99.9% of c through a universe where Alpha Centauri is only about 0.195 light-years away. At that speed, the journey takes approximately 0.195 light-years divided by 0.999 c, which works out to roughly 0.195 years, or approximately 71 days. 71 days. A trip to the nearest star system, a voyage that light itself requires more than 4 years to complete, would take the crew less than 2.5 months of experienced time. This number is not an approximation or a trick of accounting. It is the proper time of the journey, the time measured by clocks that travel with the ship, and it is the only time that has physical meaning for the crew. They age 71 days. They eat roughly 71 days of meals. They sleep roughly 71 nights. Their biological clocks, their wristwatches, and the atomic clock mounted on the instrument panel all agree. The trip took 71 days. Meanwhile, on Earth, 4 years and roughly 4 months have passed. This is time dilation, and at a Lorentz factor of 22.4, it is not a subtle correction, it is a chasm. For every single day the crew experiences on board, approximately 22 days and 10 hours elapse on Earth. For every month of ship time, nearly 2 years of Earth time vanish. The crew lives in slow motion relative to the rest of the universe, except they do not feel slow at all. From their own perspective, they are living at a perfectly normal rate. It is the universe outside that has sped up. This distinction between proper time and coordinate time is one of the most important concepts in all of relativity, and it is worth defining precisely because casual language almost always gets it wrong. Proper time is the time measured by a clock that is present at both events being compared. If you start a stopwatch when the ship leaves Earth and stop it when the ship arrives at Alpha Centauri, the elapsed reading is the proper time of the journey. It is the time experienced by anyone and anything traveling with the clock. It is frame independent in the sense that every observer in the universe agrees on what the ship's clock reads at departure and arrival, even if they disagree about how much time passed in their own frames. Coordinate time is the time assigned to those same events by a distant observer using their own clock. The Earth-based mission controller starts their clock when the ship departs and stops it when they calculate the ship has arrived, based on the known distance and velocity. That elapsed reading is the coordinate time. It is frame-dependent. Different observers in different states of motion will assign different coordinate times to the same pair of events. The critical realization is that proper time along the ship's path is always shorter than coordinate time, measured by the stationary observer. Always. This is not because the ship's clock is broken or running slow in any mechanical sense. It is because the ship's path through space-time is geometrically shorter than the stationary observer's path through space-time. Space-time is not flat in the way that three-dimensional space is flat. It has a structure called Minkowski geometry, where the longest elapsed time between two events belongs to the observer who does not accelerate. Any deviation from a straight unaccelerated path through space-time results in less elapsed proper time. This is the resolution of what is commonly called the twin paradox, and it is worth walking through carefully because it is so often misunderstood. Imagine two people. Call them the traveller and the homebody. Both are 30 years old on the day the ship departs Earth. The traveller boards the ship, the homebody stays behind. The ship accelerates to 99.9% of light speed, cruises to a star system roughly 11 light-years away, then decelerates, turns around, accelerates again, cruises home, and decelerates to a stop back at Earth. The outbound leg covers roughly 11 light-years at 0.999 c. In Earth's frame, that takes about 11 years. The return leg takes another 11 years. Total coordinate time for the round trip, approximately 22 years. During those 22 years, the homebody ages 22 years. They are now 52 years old. The traveller's experience is radically different. During each cruise phase, the Lorentz factor of 22.4 compresses the traveller's elapsed time by that factor. The cruise phases, which account for almost all of the journey, contribute roughly 22 years divided by 22.4, which gives approximately 0.98 years, or about 50 weeks of proper time for the cruise segments combined. Add some additional weeks for the acceleration and deceleration phases, where the ship was moving slower than full cruise speed and the time dilation factor was correspondingly lower. The total proper time for the round trip comes to roughly 14 months. The traveller returns to Earth biologically aged to approximately 31 years and 2 months. The homebody is 52. They stand face to face, and the age difference is real. Not psychological, not perceptual, real. The traveller's cells have divided fewer times. Their hair has grown less. Their radioactive decay clocks have ticked fewer times. Every physical process on board the ship proceeded through 14 months of evolution, while every physical process on Earth proceeded through 22 years. This is not paradoxical, even though it is called a paradox. The reason the two twins age differently is that their situations are not symmetric. The homebody remained in an inertial frame the entire time, coasting through space-time without acceleration. The traveller accelerated at departure, decelerated at the turnaround, accelerated again for the return, and decelerated at arrival. Those accelerations are physically real events. The traveller feels them as forces pressing against their body. The homebody feels nothing. The acceleration breaks the symmetry between the two frames, and is the reason one twin ages less than the other. General relativity provides the full mathematical treatment, but the basic insight is straightforward. The twin who accelerated followed a shorter path through space-time, and therefore accumulated less proper time. Before we extend these calculations to longer journeys, it is worth stopping to address a question that an attentive viewer might be asking. How do we know any of this is real? Time dilation sounds extraordinary. Length contraction sounds impossible. Are these predictions that exist only in equations, or have they been measured with actual instruments in the physical world? They have been measured, repeatedly, with extraordinary precision, and the results match the predictions of special relativity to the limits of experimental accuracy. The most famous early test was conducted in 1971 by physicists Joseph Hafele and Richard Keating. They placed 4 cesium atomic clocks on commercial aircraft and flew them around the world, once eastward and once westward. When the travelling clocks were compared to reference clocks at the United States Naval Observatory, the differences were exactly as special and general relativity predicted. The eastward clocks, which moved faster relative to the non-rotating frame, lost approximately 59 nanoseconds. The westward clocks gained approximately 273 nanoseconds. These are tiny amounts of time, billionths of a second, but they are precisely what Einstein's equations demanded. The experiment has been repeated and refined many times since, with results that consistently confirm the predictions. More dramatically, time dilation is confirmed every second of every day by unstable subatomic particles produced in Earth's upper atmosphere. When cosmic rays strike atmospheric molecules at high altitude, they produce showers of particles including muons. Muons are unstable and decay, with a half-life of approximately 2.2 microseconds, as measured in their rest frame. At the speed they travel after creation, roughly 99.9% of c, they should decay long before reaching the ground. The distance from their creation altitude to the surface is about 15 kilometers. Even at nearly light speed, traversing that distance takes roughly 50 microseconds, or more than 20 half-lives. Virtually no muons should survive the trip, yet they arrive at the surface in enormous numbers. Particle detectors at ground level record muon fluxes that are completely inconsistent with the rest frame half-life. The explanation is time dilation. In the Earth's frame, the muon's internal clock runs slow by a factor given by its Lorentz factor, roughly 22 at 99.9% of c. Its effective half-life, as measured by an Earth observer, stretches from 2.2 microseconds to roughly 49 microseconds. That is long enough for a substantial fraction to reach the ground. From the muon's own frame, it survives because the distance to the ground is length contracted by the same factor, shrinking 15 kilometers to roughly 700 meters, a distance easily crossed within the muon's normal lifetime. Both explanations are correct, both are real, and both confirm that time dilation and length contraction are not abstractions. They are physical facts measured with hardware. The Global Positioning System provides yet another daily confirmation. GPS satellites orbit Earth at roughly 14,000 kilometers per hour, and at an altitude where gravitational time dilation also contributes. The combined relativistic effects cause satellite clocks to drift by approximately 38 microseconds per day relative to ground clocks. If this drift were not corrected, GPS position calculations would accumulate errors of roughly 10 kilometers per day. The correction is applied continuously, invisibly, in every GPS receiver on the planet. Every time your phone tells you where you are, it is performing a relativistic calculation to get the answer right. These experiments are not obscure or contested. They are foundational to modern technology and have been verified by independent groups across decades. Time dilation is as experimentally confirmed as the existence of atoms. It is not a hypothesis, it is a measured feature of the universe. Now extend the twin paradox scenario to longer journeys, and the numbers become staggering. A journey to Tau Ceti, roughly 12 light-years away, would take the crew about 6 months of subjective time. Earth would experience 12 years. A trip to Vega at 25 light-years requires about 13 months aboard ship and 25 years on Earth. A voyage to a star 100 light-years distant would cost the crew roughly 4.5 years of their lives, while a full century passes at home. At each of these scales, the crew remains young while the world they came from ages and changes. The mathematics is merciless. Every additional light year of distance translates to an additional year of Earth time lost, but only an additional 16 days or so of ship time experienced. The further you travel, the more radically you are displaced in time relative to your origin. You do not merely cross space. You skip forward through everyone else's timeline while your own proceeds at its usual pace. Communication during the journey is theoretically possible, but practically agonizing. Consider the relativistic Doppler effect applied to radio transmissions. The ship is receding from Earth at 99.9% of C. A radio signal sent from the ship toward Earth gets stretched by the relativistic Doppler factor, which for a source moving directly away at this velocity works out to a redshift factor of approximately 44.7. A 1-second radio pulse transmitted by the crew arrives at Earth stretched to nearly 45 seconds. A 1-hour message broadcast at standard frequencies would take nearly 2 days to receive, and the frequencies would be shifted so far into the low-frequency radio bands that specialized antennas would be needed to detect them. The reverse is equally distorted. Signals transmitted from Earth toward the retreating ship arrive at the crew's receivers with the same enormous redshift. A daily news broadcast from Mission Control would arrive as a faint, stretched-out murmur spanning weeks of reception time. The crew could theoretically decode it, but the experience would be like listening to a conversation played at 1/45th normal speed while simultaneously pitched down by a factor of 45. The information content is preserved, but the experience of receiving it is profoundly alienating. In the forward direction, the picture inverts. If the crew sends a signal ahead toward their destination, while approaching it at 99.9% of C, that signal is blue shifted by the reciprocal factor, roughly 44.7. Frequencies jump from radio into microwave, from microwave into infrared, and beyond. A standard radio transmission aimed forward arrives at the destination as a compressed, high-frequency burst containing the same information packed into a tiny fraction of the original duration. 1 hour of crew transmission arrives in about 80 seconds of receiver time, shifted to enormously high frequencies. Any civilization at the destination receiving that signal would detect a rapid-fire chirp of high-energy electromagnetic radiation sweeping in from the direction of the approaching car's ship. They would need to know the ship's velocity precisely in order to decode the signal, because without correcting for the Doppler shift, the transmission would be unrecognizable. There is also a subtler and more disorienting consequence of the crew's contracted universe. We established that the distance to Alpha Centauri appears compressed to about 0.2 of a light-year from the crew's frame. But this contraction applies to everything along the direction of travel, not just the destination. The entire structure of the galaxy ahead of and behind the ship is squeezed along the axis of motion. Stars that are separated by light-years in the rest frame appear separated by fractions of light-years in the crew's frame. The Milky Way itself appears compressed into a thinner disk. Constellations ahead of the ship are distorted, crowded together, as if the universe is rushing toward a focal point. Meanwhile, distances perpendicular to the direction of travel are not affected. A star that is 5 light-years to the left of the ship's path remains 5 light-years to the left in both frames. Only the forward-backward axis is contracted. This creates a deeply strange spatial distortion, where the universe appears to have been run through a cosmic press, flattened along one axis, while remaining unchanged along the other two. Navigation must account for the contracted distances, the aberrated star positions, and the Doppler-shifted radiation from every object in the sky. Star maps prepared on Earth are useless along the travel axis. A navigation computer would need to apply Lorentz transformations to every catalogue entry to produce a map that matches what the crew's instruments actually detect. The distorted sky the crew observes is a combined product of relativistic aberration, Doppler shifting, and the finite speed of light. Nearly all the stars in the sky appear crowded into a brilliant disk ahead of the ship. This disk is not merely bright, it is spectrally transformed. Stars that would normally appear as dim red dwarfs are boosted into visible wavelengths. Stars that would normally appear white or blue are pushed into the ultraviolet, becoming invisible to the naked eye but blazing in UV detectors. The forward sky is a concentrated, colour-shifted tapestry of compressed starlight, while the rearward sky is a dark void containing only a few faint, deeply reddened sources. If the crew could look directly ahead through a window designed to filter the radiation into safe visible wavelengths, they would see something no human has ever witnessed. The galaxy itself, distorted and compressed, would appear to funnel toward them as if they were falling into the center of a luminous tunnel. The visual effect has been simulated in computer models, and the results are haunting. The familiar constellations are gone, replaced by a swirling concentration of light that bears no resemblance to the night sky visible from Earth. This is the seductive promise of relativistic travel, and it is not false. Time dilation and length contraction are real physical phenomena, confirmed by the experiments we have just described, and by decades of additional work in particle physics, satellite operations, and precision metrology. The physics is settled, the effects are measured, they are as reliable as gravity. And yet, everything we have described so far carries a hidden asterisk. The distances shrink, the time compresses, the stars rush toward you. It sounds almost magical. It sounds like nature is offering a shortcut through the cosmos, a loophole that allows mortal beings to cross interstellar gulfs within a human lifetime. But nature does not offer loopholes, it offers trade-offs. And the trade-off for relativistic travel is one of the harshest in all of physics. Every second of compressed time, every contracted light year, every abbreviated journey must be paid for with energy. Not modest amounts of energy, not large amounts of energy, amounts of energy so vast that they challenge the total productive capacity of human civilization. The time dilation is real. The length contraction is real. But the ticket into this regime, the price of accelerating a physical object to 99.9% of light speed, is denominated in units that make the entire endeavour seem less like a shortcut and more like a ransom demand from the universe itself. The crew aboard the ship experiences a contracted, time-dilated reality where interstellar distances are navigable and aging slows to a crawl relative to everyone left behind. That reality is beautiful and confirmed by every experiment we know how to conduct. But entering that reality requires something that no experiment has ever come close to achieving. And the cost is not merely expensive, it is, by any current measure, physically absurd. That cost is the subject of what comes next. Everything described so far is physically real. The time dilation, the length contraction, the compressed distances, the abbreviated journeys, all of it is confirmed by experiment and guaranteed by the mathematics of special relativity. But there is a reason no spacecraft has ever approached 99.9% of light speed. There is a reason no serious engineering proposal has ever targeted this velocity. And that reason is not that we lack ambition or imagination. It is that the universe charges a price for entering the relativistic regime, and the price is so staggeringly high that it makes the beautiful physics we described earlier feel almost cruel. The currency is energy, and the bill is beyond anything human civilization has ever contemplated. Start with a basic question. How much kinetic energy does a moving object carry? At everyday speeds, the answer is given by the familiar classical formula: 1/2 times mass times velocity squared. Double the speed, and you quadruple the energy. This relationship is intuitive and scales smoothly. A car moving at 60 miles per hour carries 4 times the kinetic energy of the same car moving at 30. But that classical formula is an approximation. It works beautifully at low velocities, but it quietly breaks down as speeds approach a significant fraction of c. The true formula, derived from special relativity, replaces the classical expression with something far more aggressive. The relativistic kinetic energy of an object is given by the Lorentz factor -1 multiplied by the rest mass, multiplied by c squared. At low speeds, this reduces to the classical formula. At high speeds, it diverges from it catastrophically. Here is why. As an object approaches the speed of light, the Lorentz factor grows without bound. At 90% of c, the factor is about 2.3. At 99%, it is about 7.1. At 99.9%, it is about 22.4. Each additional 9 after the decimal requires vastly more energy than the previous one. The function is not linear. It is not quadratic. It is asymptotic, meaning it curves upward toward infinity as velocity approaches c and never actually reaches the limit. This means that the energy difference between 99% and 99.9% of light speed is not 10% more effort. It is approximately 3 times more energy. And the difference between 99.9% and 99.99% is roughly another factor of 3 again. Each additional fraction of speed costs exponentially more, not linearly more. The universe does not merely make light speed expensive, it makes approaching light speed progressively more punishing with every incremental gain, and it arranges the mathematics so that actually reaching c would require infinite energy. Let us attach real numbers to this. Consider a spacecraft with a fully loaded mass of 1,000 metric tons. That is roughly the mass of the International Space Station, which is one of the largest structures humanity has ever assembled in space. It is a reasonable lower bound for any vessel designed to carry crew, life support, shielding, scientific instruments, and fuel across interstellar distances. Many credible interstellar mission concepts assume much larger masses, but 1,000 metric tons will serve as a conservative baseline. At 99.9% of light speed, the Lorentz factor is 22.4. The relativistic kinetic energy is the Lorentz factor -1, which is 21.4 multiplied by the rest mass energy. The rest mass energy of 1,000 metric tons is found by multiplying 1 million kilograms by the speed of light squared, which gives approximately 9 times 10 to the 22nd joules. Multiply that by 21.4, and you get roughly 1.9 times 10 to the 24th joules. That number requires context. The total energy consumption of human civilization in a typical recent year is approximately 5.8 times 10 to the 20 joules. The kinetic energy of our 1,000-ton spacecraft at 99.9% of c is therefore roughly 3,300 times the total annual energy output of every power plant. Every engine, every furnace, every device on the entire planet Earth combined. Not 3,300%, 3,300 times. Our single spacecraft, at cruise velocity, carries more energy than the whole of human civilization produces in 3,000 years. But it gets worse. That figure accounts only for the kinetic energy of the ship at its cruising speed. It does not include the energy needed to produce that kinetic energy. No propulsion system is 100% efficient. Rocket engines, even theoretical ones, waste energy in their exhaust, in thermal losses, in the mass of the propellant itself. Chemical rockets convert less than 1% of their fuel mass into useful kinetic energy. Nuclear fission engines do better, perhaps 1% of the fuel's rest mass energy. Nuclear fusion can theoretically achieve around 0.7%. Even matter-antimatter annihilation, the most energetic reaction known to physics, converts roughly 100% of the fuel's rest mass into energy, but delivering that energy as directed thrust to a spacecraft involves enormous losses. The rocket equation, first derived by Konstantin Tsiolkovsky in 1897, describes the fundamental relationship between a rocket's exhaust velocity, its fuel mass, and the final velocity it can achieve. For relativistic speeds, the equation must be modified to account for special relativity, producing what is called the relativistic rocket equation. the mathematics reveals a brutal truth. To accelerate a 1,000-ton payload to 99.9% of C using a matter-antimatter drive, which is the most efficient propulsion system permitted by known physics, the required fuel mass is enormous. The mass ratio, the ratio of fully fueled ship to empty ship, reaches values of approximately 45:1 for a single-stage journey that only accelerates and does not decelerate. This means the ship must carry roughly 44,000 metric tons of fuel for every 1,000 tons of payload. If the ship also needs to decelerate at the destination, which any crewed mission would, the mass ratio squares. The outbound fuel must accelerate not just the payload, but also all the fuel needed for deceleration. The result is a mass ratio of approximately 2,000:1, 2 million metric tons of matter-antimatter fuel for a 1,000-ton spacecraft, and this is with a theoretically perfect engine that has never been built and may never be achievable. The total mass of antimatter alone, which makes up half of a matter-antimatter fuel supply, would be roughly 1 million metric tons. As of today, the total amount of antimatter produced by every particle accelerator on Earth since the technology was invented amounts to a few nanograms. Not milligrams, not micrograms, nanograms. Billionths of a gram. The gap between what we can produce and what we would need is not a factor of 10 or 100. It is a factor of roughly 10 to the 21st power. 1 billion trillion. Even setting aside the problem of producing the fuel, consider the power output required during acceleration. If the ship accelerates at 1 g, a comfortable rate that simulates Earth's gravity and avoids crushing the crew, reaching 99.9% of C takes approximately 3.7 years of ship time. During those years, the engine must sustain a continuous power output that climbs into the petawatt range, thousands of terawatts, as the ship approaches cruise velocity. For reference, the total power output of the Sun is approximately 3.8 times 10 to the 26 watts. A few petawatts sounds small compared to a star, but it is roughly 1,000 times the total electrical generating capacity of planet Earth. The engine must maintain this output continuously for years without interruption, without failure, and without melting the ship around it. The deceleration phase is equally demanding. To stop at the destination, the ship must shed the same amount of kinetic energy it accumulated during acceleration. This means running the engine in reverse at the same power level for the same duration. The total energy expenditure for acceleration and deceleration combined is roughly double what was needed for acceleration alone, and the fuel mass requirements compound accordingly. Some proposals attempt to avoid the fuel problem by collecting propellant along the way. This is the concept behind the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The idea is elegant. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter. A ship equipped with a magnetic funnel thousands of kilometers across could scoop up this hydrogen and feed it into a fusion reactor, providing thrust without carrying fuel. In principle, a ramjet could accelerate indefinitely, limited only by the speed of light. In practice, the concept faces devastating obstacles. At 99.9% of C, the incoming hydrogen is not gentle fuel waiting to be collected. It is a stream of particles moving at relativistic velocities relative to the ship. Each hydrogen atom strikes the collection field with the kinetic energy of a high-energy cosmic ray, approximately 20 billion electron volts per proton. The drag created by scooping these particles out of the interstellar medium may exceed the thrust that can be produced by fusing them. Multiple analyses have concluded that for velocities above roughly 10 to 15% of C, the Bussard ramjet produces net deceleration rather than net acceleration. It becomes a brake, not an engine. The faster you go, the harder the interstellar medium pushes back against you. This brings us to the second enormous problem with traveling at 99.9% of light speed, a problem that has nothing to do with energy production and everything to do with survival. Interstellar space is not empty. It appears empty to human senses and even to most scientific instruments, but it contains a thin bath of matter that becomes extraordinarily dangerous at relativistic velocities. The interstellar medium consists primarily of hydrogen, roughly 70% by mass, with helium making up most of the rest and trace amounts of heavier elements. The average density in the galaxy is approximately 1 atom per cubic centimetre, though it varies enormously depending on location. Near our solar system, inside a region called the local bubble, the density drops to about 0.07 atoms per cubic centimetre. In dense molecular clouds, it can exceed 1,000 atoms per cubic centimetre. At low velocities, these stray atoms are utterly harmless. They bounce off spacecraft surfaces with negligible energy, too sparse and too slow to cause any measurable effect. Even at 10% of light speed, the interactions are manageable with reasonable shielding. But as velocity increases towards c, the kinetic energy of each incoming atom rises sharply. The relativistic kinetic energy of a single hydrogen atom at 99.9% of c is roughly 20 billion electron volts, or about 20 GeV. This is the energy range of particles produced by major research accelerators. Each atom in the interstellar medium becomes, in the ship's reference frame, a high-energy cosmic ray, and there are a lot of them. At this velocity, the flux of hydrogen atoms across the ship's forward cross-section is enormous. For a ship with a forward-facing area of roughly 100 square meters, even in the relatively sparse local bubble, approximately 500 trillion protons per second slam into every square meter of the hull, because Lorentz contraction compresses the gas ahead into a denser stream. Across the full cross-section, that amounts to roughly 50 quadrillion impacts per second, each one carrying approximately 20 GeV of kinetic energy. The total power deposited on the hull by this particle bombardment can be calculated directly, and the numbers are alarming. For a ship moving through the local bubble at this speed, the energy flux into the forward surface reaches several megawatts per square meter in the local bubble, and up to roughly 20 megawatts per square meter in denser regions of the interstellar medium. Research published by physicist Oleg Semyonov and by teams associated with the NASA Starlight collaboration has modeled these effects in detail. Their findings are unambiguous. At velocities above roughly 80% of c, the radiation dose from interstellar hydrogen alone exceeds lethal levels for biological organisms within seconds if the hull is not shielded. At 99.9% of c, the dose rate behind a 10-centimeter aluminum hull would deliver a fatal radiation exposure almost instantaneously. But radiation dose is only one half of the particle bombardment problem. The other half is thermal loading, and it operates under entirely separate physics. Every proton that strikes the hull deposits not just radiation but heat. At megawatts per square meter, the forward face of the ship is absorbing thermal energy at a rate that threatens the structural integrity of any known material. The hull must radiate this heat away into space, or its temperature will climb without limit until the structure fails. In the vacuum of space, the only available cooling mechanism is thermal radiation, governed by the Stefan Boltzmann law. The power radiated by a surface is proportional to the fourth power of its absolute temperature. This means that to radiate away megawatts per square meter through thermal emission alone, the hull surface must reach temperatures of several thousand Kelvin. For context, the melting point of tungsten, the most refractory common metal, is approximately 3,687 Kelvin. The melting point of aluminum is 933 Kelvin. At megawatts per square meter of incoming flux, an aluminum hull cannot radiatively cool fast enough to avoid melting. In denser regions of the interstellar medium, where the flux climbs toward 20 megawatts per square meter, even tungsten cannot survive. The equilibrium temperature required to radiate the incoming energy reaches roughly 4,400 Kelvin, exceeding the melting point of the most refractory metals known. The forward shield does not merely need to stop radiation, it needs to survive temperatures approaching those on the surface of a cool star. This thermal crisis is distinct from the radiation shielding problem and demands its own engineering solutions. Proposed approaches include ablative shields that gradually vaporize, sacrificing mass to carry heat away from the ship, and actively cooled liquid metal surfaces that circulate molten material away from the hottest regions. None of these have been tested at anything approaching the relevant energy densities. The thermal problem alone, setting aside radiation entirely, may be sufficient to render travel at 99.9% of C physically unsurvivable for any material structure. And then there is a third layer of danger hidden inside the first two. When a 20 GeV proton strikes a metallic hull, it does not simply stop and deposit its energy in a neat, localized spot. The proton is energetic enough to penetrate deep into the material and interact with the nuclei of the atoms it encounters. These nuclear interactions produce cascades of secondary particles. The incoming proton strikes an aluminum or iron nucleus and shatters it, producing a spray of lighter particles including neutrons, charged pions, kaons, and gamma-ray photons. The charged pions decay within nanoseconds into muons, which penetrate further into the hull before decaying into electrons and neutrinos. The neutral pions decay almost instantly into pairs of high-energy gamma rays that travel at light speed through the material, depositing energy along their paths. This cascade effect means that the radiation hazard is not confined to the outermost layer of shielding. The secondary particles penetrate far deeper than the original proton. A proton that stops within 10 centimeters of aluminum produces a shower of neutrons and gamma rays that continues for meters into the structure beyond. Adding more shielding does help, but with diminishing returns. Each additional meter of material absorbs some fraction of the cascade, but generates its own secondary particles in the process. The shielding problem is not linear. Doubling the thickness does not halve the radiation dose on the other side. It reduces it, but by a factor that depends on the complex physics of hadronic showers, neutron moderation, and gamma-ray attenuation through bulk matter. Effective protection against these cascades requires not just thick shielding, but layered shielding, designed with specific materials at specific depths. Hydrogen-rich materials like polyethylene are effective neutron moderators. Dense metals like lead or tungsten attenuate gamma rays. But the mass of a multi-layer shield thick enough to reduce the radiation behind it to survivable levels at this velocity would be enormous, adding thousands or tens of thousands of metric tons to the ship's mass, which in turn increases the fuel required, which increases the total mass further in a vicious cycle that makes the engineering problem exponentially harder. And hydrogen atoms are not the only threat. The interstellar medium also contains dust grains. These are microscopic particles of silicate, carbon, and ice, typically ranging from a few nanometers to a few micrometers in diameter. With masses on the order of nanograms to micrograms, they constitute roughly 1% of the interstellar medium's total mass. At 99.9% of C, a single dust grain weighing 1 nanogram carries a relativistic kinetic energy of approximately 1.9 times 10 to the 6th joules. That is roughly equivalent to the explosive energy of half a kilogram of TNT. Half a kilogram of TNT concentrated into a particle smaller than a human hair, impacting one spot on the hull at nearly the speed of light. The impact does not behave like a normal collision. At these energies, the dust grain and the hull material it strikes both undergo nuclear-scale disintegration. The grain does not bounce or embed itself. It detonates, converting its kinetic energy into a superheated plasma fireball that vaporizes the surrounding hull material and sends a shockwave of secondary particles deeper into the ship's structure. A single microgram grain, 1,000 times more massive, would carry an energy equivalent to roughly 500 kilograms of TNT. One impact from a grain that size would be catastrophic. The probability of encountering such grains depends on the path and the density of the local medium. In the relatively clean environment of the local bubble, the flux of microgram scale grains is low enough that a mission covering a few light years might not encounter one. But smaller grains in the nanogram range are far more common, and over a multi-light-year journey, thousands of impacts from particles in this size range are essentially guaranteed. Each one is a localized explosion on the hull surface. Proposed solutions to the dust problem include magnetic deflection fields to push charged particles aside before they reach the hull, physical shields made of sacrificial ablative material that erodes over the course of the journey, and flying in the wake of a leading shield that absorbs impacts while the main vessel follows at a safe distance. None of these solutions have been demonstrated at any relevant scale. Magnetic deflection works only on charged particles and is ineffective against neutral dust grains. Ablative shields add mass, which compounds the fuel problem. A leading shield separated from the main vessel introduces its own engineering challenges, including maintaining precise formation flying at relativistic speeds over years of travel time. The combined effect of hydrogen bombardment, thermal loading, secondary particle cascades, and dust impacts transforms interstellar space from a passive void into an active hazard environment. At 99.9% of C, the ship is not merely traveling through space. It is pushing through a gauntlet of high-energy radiation, searing heat, and microscopic projectiles that would destroy an unprotected vessel in moments. The very medium that appears to be empty vacuum at rest becomes, at relativistic velocities, a lethal storm that the ship must survive continuously for the duration of the cruise phase. This is not a theoretical concern dismissed by optimistic futurists. It is a central finding of every serious engineering study of relativistic interstellar travel. The Breakthrough Starshot initiative, which was the most ambitious and best-funded interstellar propulsion project in human history, targeted a velocity of only 20% of the speed of light, not 99.9%. Even at that far more modest speed, the interstellar medium posed significant challenges to the survival of the probe. The project anticipated that each square centimetre of its gram-scale spacecraft's forward surface would collide with roughly 1,000 dust particles of at least 0.1 micrometer diameter during the transit to Alpha Centauri, and Breakthrough Starshot did not survive its own engineering challenges. By September of 2025, the project was quietly placed on indefinite hold. After 9 years and approximately $4.5 million spent of the pledged $100 million, the initiative stalled. The laser array required to accelerate the light sail demanded power levels on the order of 100 gigawatts, comparable to the electrical output of an entire industrialized nation, focused into a coherent beam for minutes at a time. The sail material had to withstand the laser flux without melting, deforming, or becoming opaque. The probe had to survive the acceleration, the interstellar medium, and the 4-year transit while remaining functional enough to transmit data back to Earth from a distance of 4.37 light-years. None of these problems were solved. 30 research challenges were identified at the project's founding. After 9 years of work by 37 research groups, most remained open. Breakthrough Starshot targeted 20% of light speed for a gram-scale unmanned probe, with no deceleration and no return. The engineering was deemed premature. The technology gaps were measured in orders of magnitude. The funding, while generous by academic standards, was recognized as a fraction of what would actually be needed. 99.9% of the speed of light, for a crewed vessel with deceleration capability, is not merely harder than Breakthrough Starshot. It exists in a different category of difficulty entirely. The energy requirements are roughly 100,000 times greater per kilogram of payload. The radiation environment is approximately 1,000 times more intense. The shielding mass is many thousands of times larger. The fuel requirements, even with theoretically perfect matter-antimatter propulsion, demand quantities of antimatter that exceed current global production by a factor of more than 1 billion trillion. The fastest human-made object as of this writing is the Parker Solar Probe, which in late 2024 achieved a velocity of approximately 692,000 kilometers per hour during its close approach to the Sun. That is roughly 0.064% of the speed of light, not 0.64%, 0.064%. The gap between that number and 99.9% is not a gap. It is a canyon so vast that it redefines what the word gap means. Crossing it would require increasing the probe's velocity by a factor of more than 1,500, while simultaneously scaling up the mass by a factor of millions, and sustaining the acceleration for years rather than seconds. Every claim made here can be verified against published physics. The energy figures follow directly from the relativistic kinetic energy formula. The radiation doses are calculated from known interstellar medium densities and standard particle physics. The fuel-mass ratios derive from the relativistic rocket equation. The shielding requirements come from peer-reviewed analyses of proton penetration depths in materials. The thermal loading follows from the Stefan Boltzmann law applied to known energy flux values. The secondary cascade physics is standard nuclear and particle physics applied to proton-nucleus interactions at GeV energies. None of these results are speculative. They are consequences of established physics applied to a specific velocity, and they paint a picture that is both precise and sobering. The universe permits time dilation. It permits length contraction. It permits a crew to cross interstellar distances in weeks or months of personal time while decades pass on Earth. These are real features of space-time, offered freely to anyone who can reach the required velocity. But the universe does not offer the velocity freely. It prices the ticket in energy, in shielding mass, in thermal endurance, in engineering complexity, and in fuel quantities so extreme that they currently have no realistic path to production. The beautiful physics we explored earlier is gated behind an energy barrier of almost incomprehensible height. The ship we have been imagining, the one that compresses distance and dilates time and turns interstellar space into a navigable frontier. That ship must carry the energy output of a civilization inside its fuel tanks, survive a continuous particle beam bombardment that simultaneously irradiates, melts, and erodes its forward hull for the entire duration of its cruise, and decelerate using the same obscene quantities of energy it spent getting up to speed. If it fails at any of these tasks, the journey ends in either an explosion, a radiation death, or a flyby so fast that the destination flashes past in a fraction of a second with no possibility of stopping. That last scenario, the flyby, raises the final question of this story. Suppose, despite everything, the ship makes it. Suppose some future civilization commands the energy, builds the shielding, produces the fuel, and launches the vessel. Suppose the crew survives the acceleration, endures the cruise, and arrives at their destination. What does arrival actually look like? What does it mean to stop? And what waits for them when they finally do? The ship has survived. Against every engineering probability we just outlined, it has reached 99.9% of the speed of light, endured the radiation bombardment, maintained its shielding, and the crew is alive. Alpha Centauri lies ahead. The destination is close. The contracted distance in the crew's frame is vanishingly small. The 71 days of ship time are nearly over. Now the ship must stop. This is the problem that most popularized accounts of relativistic travel either ignore or dismiss with a sentence. Getting up to speed was one half of the energy nightmare. Stopping is the other half. And stopping is, in certain ways, harder than accelerating, because the physics does not care that you have already spent an unthinkable quantity of fuel to reach cruise velocity. It demands the same payment again to take that velocity away. At 99.9% of light speed, the ship carries approximately 1.9 times 10 to the 24th joules of kinetic energy per 1,000 metric tons of mass. That energy must be removed from the ship before it can enter orbit or rendezvous with anything at the destination. If the ship simply coasts through the Alpha Centauri system without decelerating, the transit time across the habitable zone of the nearest star, Proxima Centauri, would be measured in fractions of a second. At 0.999 C, the ship covers 1 astronomical unit, the distance from Earth to the Sun, in approximately 8 minutes and 20 seconds. The habitable zone around Proxima Centauri, a red dwarf far dimmer than the Sun, extends from about 0.04 to 0.08 astronomical units from the star. The ship would cross the entire habitable zone in roughly 20 to 40 seconds. 40 seconds. After 71 days of travel, after years of planning and construction, after an investment of energy that dwarfs the output of civilizations, the crew would have 40 seconds in the vicinity of a potentially habitable planet before the system recedes behind them at 669 million miles per hour. No meaningful observation could be conducted. No orbit could be entered. No landing could be attempted. The ship would flash through the target system like a bullet through a soap bubble and continue into the void beyond, carrying its crew toward nothing, with no fuel to turn around and no destination ahead. This is why deceleration is not optional. It is the difference between a mission and a catastrophe. Decelerating from 99.9% of C to a dead stop requires the ship to shed the same kinetic energy it accumulated during the acceleration phase. If the propulsion system is a rocket of any kind, this means carrying enough fuel to produce the same total impulse in reverse. We discussed the mass ratios earlier. For a matter-antimatter drive, the fuel requirement for acceleration alone demands a mass ratio of roughly 45:1. Adding deceleration squares this ratio, pushing it to approximately 2,000:1. The ship must launch from Earth carrying 2,000 times its empty mass in fuel, most of which exists solely to slow the vessel down at the other end. This compounding is a consequence of the rocket equation's exponential nature. The fuel needed for deceleration must itself be accelerated during the first phase of the journey, which means carrying additional fuel to accelerate the deceleration fuel, which means additional fuel for that, cascading outward in a geometric series that inflates the initial mass to absurd proportions. A 1,000-ton spacecraft requires approximately 2 million metric tons of total launch mass. This is not a marginal engineering challenge. It is a structural impossibility with any currently conceivable material or construction method. Some theoretical proposals attempt to break this cycle by decoupling the acceleration and deceleration systems. One approach uses a powerful laser array at the point of origin to accelerate the ship via light sail during departure, eliminating the need to carry acceleration fuel. The ship then carries only deceleration fuel, reducing the mass ratio from 2,000:1 down to roughly 45:1. This was the philosophy behind Breakthrough Starshot, though that project aimed at only 20% of C and did not plan for deceleration at all. Another proposal, suggested by physicist Robert Forward in 1984, uses a two-stage light sail. The outer ring of the sail detaches at the midpoint, reflects the laser beam back onto the inner sail, and decelerates it. This eliminates onboard fuel entirely, but requires a laser of extraordinary power, maintained continuously for years, beamed across light years of space with a pointing accuracy measured in nanoradians. No such laser exists. The power requirements for a crewed vessel at 99.9% of C would exceed the output of the Sun by a significant margin, directed into a coherent beam that does not diverge appreciably over interstellar distances. The engineering is not merely difficult, it is, by any present standard, physically unachievable. A third option involves using the interstellar medium itself as a braking mechanism, a magnetic sail, a large loop of superconducting wire generating a magnetic field hundreds of kilometers in diameter, could deflect the charged particles in the interstellar medium and use the resulting drag to decelerate the ship. This concept has some theoretical merit for velocities below roughly 10 to 15% of C. At 99.9%, the incoming particle energies are so extreme that the magnetic field required to deflect them would need to be enormously powerful, and the structural loads on the sail would be punishing. The same interstellar hydrogen that serves as a radiation hazard could theoretically serve as a brake, but the engineering to harness it at these velocities has never been demonstrated, even in preliminary calculations that produce optimistic results. Suppose, nevertheless, that the ship decelerates successfully. Some combination of fuel, external beaming, and magnetic braking brings the vessel to a relative stop within the Alpha Centauri system. The crew is alive. The ship is intact. They have arrived. What greets them is not a welcome party. It is a set of problems that no amount of relativistic physics can solve. The crew has reached the nearest star system to Earth, a triple star configuration consisting of Alpha Centauri A, Alpha Centauri B, and the distant red dwarf Proxima Centauri. Proxima hosts at least one confirmed planet in its habitable zone, Proxima Centauri B, a rocky world roughly 1.2 times Earth's mass, orbiting its dim parent star once every 11.2 days. From Earth, this planet has been studied only through indirect methods, radial velocity measurements and transit photometry that reveal its mass and orbital period, but almost nothing about its surface conditions. The crew is about to become the first observers to see this world directly, and what they find will determine whether the mission was worth its staggering cost. But they arrive with finite resources and no resupply chain. Every kilogram of food, every litre of water, every spare component and medical supply was loaded years ago by a civilization that has no idea whether the ship survived the journey. The crew cannot call for help. They cannot order replacement parts. They cannot receive updated instructions based on new discoveries made on Earth after their departure. They are, in the most complete sense imaginable, on their own. If Proxima Centauri B turns out to be a barren rock scoured by stellar flares, the crew must decide what to do with whatever resources remain. Do they survey the rest of the system and look for alternative targets? Do they attempt to establish a minimal outpost using whatever raw materials they can extract from local asteroids or the planet's surface? Do they begin the return trip, spending another civilizational quantity of fuel to reach cruise speed again and arrive back at an Earth that has aged decades in their absence? If the planet shows signs of habitability, the challenges multiply rather than diminish. Landing on an alien world requires atmospheric entry vehicles, surface habitats, life support systems designed for unknown chemistry, and contingency plans for biological hazards that no one on Earth could have anticipated. Every piece of that equipment was designed and built based on incomplete data gathered from 4 light-years away, using instruments that could not resolve surface features. The crew must improvise, adapt, and make irreversible decisions with no possibility of consultation. This is the operational reality that hides behind the elegant physics of time dilation and length contraction. The equations guarantee that the crew can get there in 71 days of personal time. They say nothing about what happens after arrival. The mission does not end when the ship stops, it begins. And it begins in total isolation, with no backup, no communication faster than the speed of light, and no guarantee that the destination offers anything worth the price that was paid to reach it. The first and most disorienting reality after arrival is temporal. The crew's clocks show that approximately 71 days have passed since departure, but if they point a radio telescope back toward Earth and listen, they hear nothing recent. The most recent signals reaching them from Earth were transmitted roughly 4.37 years ago, which is the light travel time between the 2 star systems. And those signals describe an Earth that launched them 4 years and 4 months ago by Earth's calendar. The crew departed roughly 4 years and 4 months in Earth's past, as measured by Earth's clocks. News, culture, politics, technology, all of it is more than 4 years out of date by the time any signal reaches them. If the crew immediately transmits a message announcing their arrival, that message travels back toward Earth at light speed and arrives approximately 4.37 years later. On Earth, the mission clock now reads roughly 8 years and 9 months since launch. Nearly 9 years have passed on Earth since the crew said goodbye, but only 71 days have passed for the crew. The people who built the ship have aged 9 years. The crew's children, if they had any, are 9 years older. Relationships, careers, governments, and technologies have evolved through nearly a decade of change. All of it invisible to the crew, until signals carrying that information crawl across the interstellar gap at the plodding pace of light. If Earth sends a reply to the crew's arrival message, that reply takes another 4.37 years to reach Alpha Centauri. By the time the crew receives a response to their announcement, roughly 13 years have elapsed on Earth since departure. 13 years of Earth time for a single exchange of messages. A conversation with mission control at this distance is not delayed. It is archaeological. Each reply describes a world that no longer exists by the time it is received. For longer missions, the temporal displacement compounds into something that can only be described as exile. Consider a crew that targets a star 50 light-years from Earth. At 99.9% of C, the outbound journey takes approximately 2.2 years of ship time. The crew arrives having aged about 2 years. On Earth, more than 50 years have passed. Everyone who waved goodbye is now 50 years older. Many are dead. The mission was launched during a different generation. If the crew immediately sends a message home, it arrives 100 years after launch by Earth's calendar. The reply, if anyone still remembers to send one, arrives 150 years after launch. The crew is not merely far from home, they have been catapulted forward in time. They left a world that existed 50 years ago, and they cannot return to it. The world they knew is gone, replaced by a society that has experienced half a century of change. If they make the return trip, another 2.2 years of ship time pass, but another 50+ years of Earth time elapse. They arrive home roughly 100 years after they left, biologically aged only 4.5 years. Their great-great-grandchildren might be alive to greet them, but nothing else about the world would be recognizable. This temporal one-way valve is intrinsic to relativistic travel. It is not a side effect or a complication. It is the central feature. Time dilation does not merely alter the relationship between the traveler and their origin, it severs it. The further you travel, the more completely you are cut off from the era you departed. At 99.9% of C, even a trip to the nearest star creates a temporal gap measured in years. A trip to a moderately distant star creates a gap measured in decades. A trip across the galaxy creates a gap measured in millennia. This has profound implications for any realistic mission architecture. A crew that accepts a relativistic mission to a star 50 light-years away is not merely volunteering for a dangerous journey. They are volunteering to leave their historical period. They are choosing to abandon every person, institution, and cultural context they have ever known, not through distance alone, but through the irreversible passage of time for everyone except themselves. The mission is not a trip, it is an emigration from an era. Any civilization contemplating such missions would need to grapple with questions that go beyond engineering. Who volunteers to leave their century behind? What legal framework governs the rights and obligations of people who return to a society that has evolved beyond their understanding? What happens to mission objectives that were defined by a civilization that no longer exists by the time the mission completes? If the crew discovers something extraordinary at their destination, the report does not reach home for decades. By the time it arrives, the sending civilization may have already discovered the same thing independently, or may have collapsed, or may have evolved interests so different that the discovery no longer matters. These are not idle philosophical diversions. They are operational constraints that shape mission design as concretely as fuel mass and shielding thickness. A relativistic mission to a star 100 light-years away must be designed to function autonomously for the crew's entire lifespan, because no meaningful support or guidance can arrive from Earth within any useful time frame. The crew must carry not just fuel and food and equipment, but an entire self-sustaining institutional framework capable of making decisions without input from a home world that has, for all practical purposes, ceased to be relevant. Now step back from the mission specifics and consider what all of this physics reveals in total. At 99.9% of light speed, special relativity delivers on its most extraordinary predictions. Time genuinely dilates by a factor of 22.4. Distances genuinely contract by the same factor. A crew can cross interstellar gulfs in weeks or months of personal time, while years or decades pass in the rest of the universe. The twin paradox is real and measurable. The visual distortion of the sky, the Doppler shifting of communications, the contraction of the cosmos along the direction of travel, all of it is confirmed physics, as solid as gravity and electromagnetism. But the same physics that enables these effects also enforces costs so extreme that they make the journey a practical impossibility by any standard humanity currently possesses. The kinetic energy required exceeds the total energy output of civilization by a large factor. The fuel mass, even with theoretically perfect propulsion, dwarfs the payload by a ratio of thousands to 1. The interstellar medium, benign at low velocities, becomes a continuous particle beam weapon at relativistic speeds, requiring shielding of a thickness and mass that compounds the fuel problem still further. Deceleration doubles the energy bill. Communication with home is stretched across years and decades, and the temporal displacement of the crew from their origin is permanent and irreversible. The central thesis of this story is not that relativistic travel is impossible. Special relativity does not forbid it. There is no law of physics that says a ship cannot reach 99.9% of C. The barrier is not theoretical, it is practical. The universe allows the journey in principle, but prices it so far beyond current capability that the gap between permission and execution spans many orders of magnitude. This distinction matters because it tells us something important about the nature of physical law. The universe is not arbitrary in its restrictions. It does not simply prohibit high velocities the way a speed limit sign prohibits driving fast on a highway. Instead, it constructs a cost function that rises asymptotically toward infinity as velocity approaches c. You can go faster. You can always go a little faster, but each increment costs more than the last, and the cost grows without bound. The speed of light is not a wall. It is a hill that gets steeper the higher you climb, and its slope approaches vertical as you near the summit. To appreciate just how steep that hill becomes, consider what different velocities actually buy you for the same journey. A trip to Alpha Centauri at 4.37 light-years. At 10% of the speed of light, the trip takes roughly 43.7 years as measured from Earth. The Lorentz factor is only 1.005. Time dilation is negligible. The crew age is almost the same amount as everyone on Earth. The energy cost is substantial but does not require exotic physics. This is the regime where fusion propulsion might someday operate. At 50% of C, the Earth frame travel time drops to about 8.7 years. The Lorentz factor rises to 1.15. The crew experiences about 7.6 years, saving roughly 1 year compared to Earth. The energy cost is already enormous, roughly 30 times what 10% of C demands per kilogram, but the time savings are modest. At 90% of C, the Earth frame time falls to about 4.9 years. The Lorentz factor is 2.3. The crew age is roughly 2.1 years. Now time dilation is noticeable. You have shaved the crew's experience from decades down to a couple of years, but you have paid dearly for it. The kinetic energy per kilogram is roughly 9 times greater than at 50% of C. At 99% of C, the Earth frame time drops to about 4.4 years. That is only half a year less than at 90%. But the Lorentz factor has jumped to 7.1, meaning the crew experiences only about 7.5 months. The energy per kilogram has nearly quintupled compared to 90%. At 99.9% of C, the Earth frame time is approximately 4.37 years, essentially the light travel time itself. You cannot meaningfully improve on this, no matter how much faster you go. But the Lorentz factor has leapt to 22.4, compressing crew time to roughly 71 days. The energy cost has tripled yet again relative to 99%. Here is the critical pattern. Between 90% and 99.9% of C, the Earth frame travel time improved by only about 6 months. A distant observer watching the ship would barely notice the difference. The ship arrives at roughly the same time, regardless of whether it was traveling at 90% or 99.9%. But the energy required increased by roughly a factor of 16, and the crew's experience time dropped from 2 years to 71 days. This reveals the peculiar economics of extreme relativistic travel. You are not paying for faster arrival as measured by the rest of the universe. You are paying for less experience time aboard the ship. The benefit is entirely internal to the crew's reference frame. The universe charges a civilization-scale energy premium not to get there sooner by outside clocks, but to let the travelers age less while getting there. Time dilation is the product you are purchasing, and its price increases without limit as you approach C. This asymptotic structure has a deep consequence for how civilizations relate to the cosmos. Any species that masters energy at the scale of its parent star could, in principle, accelerate small payloads to significant fractions of C. A Kardashev Type 2 civilization, one that harnesses the full energy output of its star, might push probes or even small crewed vessels into the relativistic regime, but 99.9% of C requires energy budgets that press even stellar-scale resources. And each additional 9 after the decimal, each step from 99.9 to 99.99 to 99.999, demands roughly another factor of 3 in energy, while yielding diminishing returns in time dilation and length contraction. The universe offers an asymptotic approach to light speed, not a threshold to be crossed, and the economics of that approach ensure that the most extreme relativistic effects remain permanently expensive. This is what makes the Lorentz factor such a powerful lens for understanding the cosmos. At everyday speeds, the factor is 1 and physics is Newtonian. At moderate relativistic speeds, say 10 to 50% of C, the factor is between 1 and 1.2, and the effects are measurable but modest. At high relativistic speeds, 90 to 99% of C, the factor ranges from about 2 to 7, and the effects become dramatic. At extreme relativistic speeds, 99.9% and beyond, the factor exceeds 20, and the effects dominate every aspect of the journey. Each regime represents a qualitatively different relationship between a traveler and the universe, and each regime is more expensive to enter than the last. The Parker Solar Probe, the fastest macroscopic object humanity has ever built, operates at a Lorentz factor so close to 1 that the difference is undetectable without atomic clocks. It exists firmly in the Newtonian regime. The protons circulating in the Large Hadron Collider operate at Lorentz factors of roughly 7,000, deep in the ultra-relativistic regime, but they are individual subatomic particles with negligible mass. Scaling those energies to macroscopic objects, to ships and crews and cargo, requires an increase in total energy that spans dozens of orders of magnitude. The physics is the same. The engineering is not. In 2025, a team in Vienna photographed the Terrell-Penrose effect for the first time by simulating relativistic motion with ultrafast lasers and picosecond cameras. It took more than 60 years from prediction to observation, not because the physics was uncertain, but because creating the conditions for observation was extraordinarily difficult even in simulation. That experiment used clever optical techniques to mimic a speed of 99.9% of C for a stationary object. No laboratory on Earth can accelerate even a milligram to 1% of light speed, let alone push a macroscopic object to 99.9. Actually achieving that speed with a real crewed vessel remains beyond anything our species can currently do or plausibly plan. Breakthrough Starshot, as we saw, could not reach even 20% of C with a gram-scale probe before the effort stalled. The target velocity was roughly 1/500th of what we have been discussing. The payload was roughly 1/1000th the mass, and even that far more modest goal proved too difficult for the most ambitious interstellar project ever funded. These facts are not reasons for despair. They are reasons for honesty. The physics of relativistic travel is among the most beautiful and well confirmed in all of science. Time dilation has been measured with atomic clocks on aircraft, on satellites, and in particle accelerators. Length contraction is confirmed every time a beam of unstable particles survives longer than its rest frame lifetime would permit. The relativistic energy-momentum relation is tested billions of times per day in every particle physics laboratory on Earth. None of this is in doubt, but the distance between confirmed physics and practical engineering is, in this case, measured not in decades of development, but in civilizational leaps of capability. Reaching 99.9% of C with a crewed spacecraft requires energy production and storage technologies that exceed current human capacity by factors of millions. It requires shielding against a radiation environment that would destroy any existing material in seconds. It requires fuel in quantities that cannot be produced by any known industrial process, and it requires a willingness to accept temporal exile as the cost of arrival. The universe is not hiding these requirements. The equations are clear, the numbers are calculable. Anyone with a textbook on special relativity and a calculator can verify every figure presented in this story. The Lorentz factor at 99.9% of c is 22.4. The time dilation is a factor of 22.4. The kinetic energy of a 1,000-ton ship is approximately 3,000 years of total global energy consumption. The interstellar hydrogen flux at the forward hull delivers a lethal radiation dose in moments without shielding. The fuel mass ratio for a decelerating mission exceeds 2,000 to 1. These are not estimates or guesses. They are the outputs of equations that have been tested and confirmed for more than a century. What this means, ultimately, is that the universe has made a very specific offer to any species that discovers special relativity. You may compress time, you may contract distance, you may cross interstellar space within a single lifetime if you wish, but you must pay for the privilege with energy on a scale that matches the cosmic distances you seek to cross. There are no shortcuts. There are no loopholes. The dilation is real, but so is the price. And the price scales with the very factor that makes the journey worthwhile. The stars are not unreachable, they are merely expensive. And the expense is not denominated in money, or political will, or technological cleverness. It is denominated in joules, in the fundamental currency of physical reality, and the universe does not negotiate on price. This is the deepest lesson of 99.9% of light speed. Not that time is flexible, though it is. Not that distance is negotiable, though it is. But that the cosmos enforces a brutal and precise honesty about what it takes to move through space-time at velocities where its most extraordinary features become manifest. The effects are real, the costs are real, and the gap between knowing the physics and commanding the energy to exploit it may be the most important measure of where a civilization stands in its relationship with the universe it inhabits. We began with a number, 99.9%. It sounded close to the speed of light, almost there, just 0.1% short of the ultimate limit. By now, that tiny gap has revealed itself to be among the most consequential fractions in all of physics. It is the fraction where time bends, where distance yields, where energy costs explode, where empty space becomes lethal, and where the universe draws a line in the mathematics and says, "You may come this far, but only if you can afford it. The stars will wait. They have been waiting for billions of years. The question has never been whether the physics permits the journey. It does. The question is whether any civilization, anywhere, ever accumulates the energy and the engineering to pay the fare. And if one does, they will discover something the equations already promise. The universe at 99.9% of light speed is not merely fast. It is a different physical regime, beautiful and terrifying in equal measure, where time and space and energy conspire to make interstellar travel simultaneously possible and almost impossibly hard. That is what actually happens if a ship travels at 99.9% of the speed of light.